Now we need to take some time and discuss a very important topic, sensitivity and specificity. This is particularly important for people in the judicial system, legal system, medical testing, tox screening, all that stuff. Now we've seen contingency tables before, and we're going to look at them some more. Here we're looking at it for when you're testing for certain outcomes. So this is the contingency table for when you're testing for a particular trait or disease or a drug, that kind of thing. So they could have the trait and they could test positive for that trait. Great. They could have it but test negative. That's a false negative. They could not have the trait and then test positive, which is a false positive, not so good. And they could not have it and test negative, which is a true negative. Now, these people are all the people that test positive. So A and B together, that gets you your row total. These are all the people that test negative, C and D. But this column is all the people that truly have the trait. Some of them tested positive for it, some of them didn't, but they're the ones that have it, so that's A plus C. And these are the ones that do not have the trait, B plus D. Some of them didn't test negative and some of them did. Now, it's kind of confusing in the abstract, so let's look at it for an example. So a medical testing company wants to verify the quality of their screening test for diabetes on a known population of patients. Right, it has the following results. So we've got our testing here. So we have 150 people tested positive for diabetes, 10 people tested negative, right? Or excuse me, tested positive but are actually diabetes negative, excuse me. These are all the people that test positive. So that's 160 total. Okay? Then all the people that test negative would be 840. All the people that truly are positive is 170. And all the people that truly are negative is 830, which gives us a grand total of 1,000. If you add up 160 and 840, you get 1,000. If you add 170 and 830, you get 1,000. Okay, what proportion of the total population truly has diabetes? All right, truly has the trait, truly has diabetes is right here. That's 170 out of the 1,000 people total. So that would be 170 out of 1,000. Which is 0.17. So far, so good. Seems pretty simple. So now it says if a patient has diabetes, okay, well, has diabetes means you're looking only at this column over here. What is the probability that they will correctly test positive? In other words, they're asking for a conditional probability. What are the chances of testing positive given that they have diabetes, given that they are diabetes positive? Well, that's 150 that would test positive out of 170 that are positive. So that's 150 divided by 170, which is about 0.882 or so. Now, what we just did there is called something special. This is called the sensitivity of a test. And the way you find it in this given scenario is A divided by A plus C. So we took cell A, which was the true positives, and we divided it by A plus C, all the people that actually have the trait, whether they tested positive or not. Right? That's the sensitivity of a test. It's the chances of testing positive given that they are positive, right, and have the disease, the drug, the trait, the whatever. All right, now if a patient does not have diabetes, what is the probability they will correctly test negative? Well, that's if they don't have diabetes, that means you're talking about this column over here. And what is the chances of correctly testing negative? That's 820 divided by the 830 total. All right, that's 820 divided by 830. That's the probability of testing negative given that you already are diabetes negative in real life. That's called the specificity of the test. And it's found by taking, let's see, letter D divided by B plus D. Right? We took all of the people that do not truly have diabetes, that's B plus D, and we found the ones that test negative in that group. That's 820 divided by 830. In other words, the true negatives divided by the total for that column. All right, now what if a patient's test is positive? What's the probability that they actually do have diabetes? All right, so they tested positive. That means you're looking at this row right here. The chances of them having diabetes is 150 divided by 160. All right. So the probability they have diabetes given that they tested positive. So that's called the positive predictive rate. It's saying, given that you tested positive, what's the chances you really are positive? Right? Given that you tested positive, get it? It's a conditional probability. So it's 150 divided by 160, which is 0.9375. And again, that's called the positive predictive rate. And last but not least, you guessed it, the negative predictive rate. So let's get that one in. So that's going to be the chances that they are truly negative given that they test negative. So their test is negative. What's the chances they truly don't have the disease? Okay, well, they tested negative, meaning you're in this row. So not having disease is 820 divided by the 840 that tested negative. Okay, and that's called the negative predictive rate, that chances you do not have diabetes given that you test negative, right? And that's found by taking cell D, the true negative rate, and dividing it by C plus D, right, which is that row for testing negative. All right, so you've just learned 4 very important terms, especially for medical testing and virus testing, even on software and on people. Important stuff. So let's put these all together into a big definitions box. All right, so we have a couple things. First thing we need to know is something called the prevalence or the prevalence rate. It's the proportion of the population that has a specific characteristic. This value is often unknown, but once we hit chapter 9 and 10, we're going to start assuming it's a certain value, and we'll learn more about that later. So for example, we assumed 17%, the proportion of the population that has the diabetes. So if we want to call this is called the prevalence rate, right there. And we can find it by taking A plus C, right, the column total, and dividing it by the grand total. That's your prevalence rate, right? The percentage of your population that either you know has your trait or disease or whatever you're looking for, or you assume it to be a certain value. So in our example, it was letter A. All right. And we found it by using A plus C and dividing it by the grand total. Okay, now the sensitivity is known by a lot of names. It's called the true positive rate, also called the power, the recall, the probability of detection of a test. It's the chances, the proportion of people who have the disease that correctly test positive. It's a very important thing to know, especially in medical testing, but actually in all sorts of things, right? What's the chances of your test truly finding the trait you're looking for? Even if it's genetic testing, that kind of thing. So in our example, that was letter B. It's kind of like I organized it that way, right? So letter B is the sensitivity. It was 0.882, 88.2%. And we found it by taking A and dividing it by A plus B, or excuse me, A plus C. Now keep in mind, if you have a test that has a high sensitivity, right, a high true positive rate, you're really catching the people that have this trait and telling them they have this trait. That means you're going to have a low false positive rate, right? Because the higher your true positives are, then the lower your false positives are going to be, right? So high sensitivity leads to low false positives. All right, then you have your sensitivity, which is your true, sensitivity is true positive, Specificity is true negative, right? It's the proportion of people who really don't have the disease or trait you're looking for that correctly test negative. Also a very nice thing. We want that to be high, right? And in our example, it was letter C. It was 98.8%, so very, very high. It often is higher in medical testing for various reasons. It's often higher to have a true negative rate than it is to have a true positive rate. And again, you can take medical classes to find out why that is. I could explain it in statistics, but it wouldn't mean much to you at this point. So this was found by taking D and dividing it by B plus D. Now keep in mind, if your true negative rate is high, that means you're going to have a low false positives, which is a good thing, right? False negatives, right? You're truly telling people that are not sick or don't have this disease or trait that they don't have it. That means you're not going to get a lot of false negatives because you're getting a lot of true negatives, right? So there's the sensitivity. Sensitivity is true positive, right? The probability of detecting the trait, the disease, the whatever. All right, specificity is the probability, if you will, of not detecting or disease when it's truly not there, right? So it's correct negative testing, true negative testing. Now, there's a relationship going on here, right? And I guess I am going to explain it right now, just in a little bit. There's a trade-off in a lot of testing, not always, but in a lot of testing between sensitivity and specificity. They're inversely related to some degree. There's a little bit more going on, obviously, and the more advanced you get in medicine and statistics, the more you can get involved in this. But for our purposes, just realize that what's going to happen if you have high sensitivity, you're going to have low false positives, but you're going to have high false negatives, and vice versa. Right? In order to lower your false positives, you're going to let your false negatives go really high, and vice versa. Right? There. In order to lower our false positives, we raise our sensitivity of our test. We want to make it so that we don't tell anyone unnecessarily that they have disease. Right? So we want to make a very low false positive rate. Right? The people that we tell are positive, they really are positive. Right? For sure. But realize what that means. If you're lowering your false positive, you're telling people, nope, you don't have it. No, you don't have it. No, you don't have it. But by doing that, you're getting more negative results, which means you're raising your chances of false negatives, right? They're on an inverse relationship, a kind of a teeter-totter, a seesaw together, right? If you raise your sensitivity, then your specificity is going to go down. Right? You're so concerned about false positives that you're going to lower your raise your false negatives, and vice versa. So you can say, okay, let's do the reverse. I want to lower my false negatives, so I'm going to increase my specificity because I want to not have any false negatives out there. Well, if that's the case, then I'm going to tell a lot more people that they're sick than actually are because I'm going to boost how many positive results I'm giving out. Right? In order to not give negatives, I'm going to give positives. But that means I'm going to increase my false positive rate. Right? So they go hand in hand, kind of like a teeter-totter. All right, now the positive predictive value, that's the probability that subjects with a positive screening test truly have the characteristic. And in our example, it was letter D, 0.9375, so 93.75%. There we have it. So we found that by taking A and dividing by A plus B. And then our negative predictive value was letter E, and that was 97.62%. And that would be taking cell D and dividing it by C plus D. One other comment real quick about this relationship between sensitivity and specificity, because it's an important one. In medicine, in particular, we usually prefer false positive to false negatives. In other words, we don't want people who are truly sick walking around thinking they're fine, because that can lead to bad behavior, poor choices, etc. We would rather tell them, yes, you have the disease, and do another test, different types of tests, and get it ruled out later at a later date. I know it seems cruel because that means you can, be told that you have, a terrible disease when you don't really have it. But at least then you're getting treatment and you're seeing doctors, right? So in medicine, a false negative is preferable, a false positive is preferable to a false negative. So I just added that note right there because that's an important point. I know it seems weird, but we would rather tell people they're sick that really aren't than have people that truly are not sick or truly are sick walking around thinking they're not, because that can lead to poor choices. All right. I'll see you back here for more lectures later.